Hi, my name is Jeremy Smith, and today I will be providing a proof for my number theory class this semester, summer of 2018. The goal of this proof is to show that the Diophantine equation x to the fourth plus y to the fourth equals z squared has no solutions. We will actually be disregarding the trivial solution where x, y, and z all equal 0 and just be focusing on non-trivial solutions in this case. We'll do this by assuming that it does exist a solution to this equation. We'll then apply Pythagorean triplets, which were derived in class this semester. And after some algebraic manipulation, we will arrive at a contradiction of the well-ordering principle. First, we will assume that there exists a solution to this equation. We recall that the form x squared plus y squared equals z squared has been solved when the GCD x, y, and z equals 1. So we'll rewrite our equation in this format of x squared squared plus y squared squared equals z squared, in which we will let the GCD of x squared, y squared, and z equal 1. Again, we recall that the Pythagorean triplets, where x squared plus y squared equals z squared, is shown to have solutions as follows, where y equals 2mn, x equals m squared minus n squared, and z equals m squared plus n squared, where m and n are positive integers and m is greater than n. We'll next apply the Pythagorean triplets to our equation x squared squared plus y squared squared equals z squared, and we'll see that y squared equals 2mn, x squared equals m squared minus n squared, and z equals m squared plus n squared, where m and n are positive integers and m is greater than n. Also, that the GCD of m and n equals 1. If you look at equation 2, we'll see that equation 2 implies the following equation, that x squared plus n squared equals m squared. We'll notice that we can again apply the Pythagorean triplets to this equation. If we do so, we find that n equals 2 alpha beta, x equals alpha squared minus beta squared, and m equals alpha squared plus beta squared, where alpha and beta are positive integers, alpha is greater than beta, and the GCD of alpha and beta equals 1. Now we have the following 6 equations. Equations 1, 2, and 3 give you x, y, and z in terms of m and n, and equations 4, 5, and 6 give you n, x, and m in terms of alpha and beta. We will then substitute equations 4 in equation 6 in equation 1, and we will see that we have y squared in terms of alpha and beta, such that y squared equals 4 alpha beta times quantity a squared plus beta, alpha squared plus beta squared. Again, we see here that the GCD of alpha and beta is equal to 1, and this implies the following, that the GCD of alpha and alpha squared plus beta squared equals 1, and the GCD of alpha squared and beta also equal 1. And we will explore this in the next slide. If you take the GCD of alpha and alpha squared plus beta squared equal to k, then we know that alpha equals ck. Similarly, we know that alpha squared plus beta squared equals dk. Therefore, if you do some substitution, we see that beta squared equals dk minus ck squared. And we can factor that so that k times quantity of d minus c squared k, we see that k divides beta squared. Therefore, we know that alpha and beta do in fact have a common divisor, namely k. But because we know that the GCD of alpha and beta is 1, we know that k is 1. Therefore, this forces alpha, beta, and alpha squared plus beta squared to all be relatively prime. Next, we take notice that y squared itself is a perfect square. We recognize that the prime factorization of a perfect square, each of the factors must appear an even number of times. Because alpha, beta, and alpha squared plus beta squared are all relatively prime, it must be the case that each of these factors are themselves perfect squares, so that the prime factorization of y squared is this right here. Because we know that alpha, beta, and alpha squared plus beta squared are all perfect squares, let us choose arbitrary numbers to be alpha equals x1 squared, beta equals y1 squared, and alpha squared plus beta squared equals z1 squared. We'll substitute equations 8 and 9 into equation 10, and we will arrive at the following equation. X1 to the fourth plus y1 to the fourth equals z squared. After taking the square root of both sides, we see that z1 equals the square root of x1 to the fourth plus y1 to the fourth. Next, we will substitute equations 4 and equation 6 into equation 3. And we'll see that z equals alpha squared plus beta squared squared plus 2 alpha beta squared. Now we substitute equations 8, 9, and 10 into equations 13. And it yields us that z equals z1 to the fourth plus 4x1 to the fourth, y1 to the fourth. We now have these 14 equations, and we will particularly be looking at equation 12 and equation 14. So we'll compare equation 12 to equation 14, and we'll see that z1, which equals the square root of x1 to the fourth plus y1 to the fourth, is less than z1 to the fourth plus 4x1 to the fourth, y1 to the fourth. So here we see that z1 is less than z. If we repeat this argument for all z sub n, which are positive integers, where n itself is also a positive integer, we receive the following set. The set containing all values of z sub n, where z is greater than z squared is greater than z to the third, z is greater than z sub 2, which is greater than z sub 3, all the way out to zn. We'll notice that the set z sub n is an infinite subset of R, which is bounded from below by 0, because all values of z sub n are values of the positive integers. Therefore, by the well-ordering principle, we see that there must exist a minimum value for z sub n, for this set. That's the definition of the well-ordering principle. However, if we observe z sub n, that set, we'll see that z sub n plus 1 is less than z sub n for all n's which are positive integers. Therefore, we see that this particular set has no minimum value. And this itself is a contradiction of the well-ordering principle. Our conclusion. Our conclusion is that our hypothesis that x to the fourth plus y to the fourth equals z squared is solvable results in a contradiction. Therefore, x to the fourth plus y to the fourth equals z squared has no solutions. Thank you.